Hello, welcome back. Today we are going to be talking about another electron trend. We are going to be talking about ionization energy. Now, if you remember from the previous video, we talked about electron affinity. And the long definition was the tendency for atoms to keep their electrons. And we do want to know kind of that full definition, but I also want to give you kind of a summary page about what's the big ticket word in the definition. Well, in electron affinity, what we are focusing on is keeping electrons. So electron affinity is all about the tendency to keep those electrons. Ionization energy is similar, and in fact, it actually follows the exact same trend. It's just focusing on a different relationship. So electron affinity was all about keeping. Ionization energy is all about removing. So ionization energy is the energy required to remove an electron. And I want you to denote the important word somehow. We're talking about removing. They go hand in hand. So atoms with high electron affinity, atoms that tend to keep their electrons, are also going to have high ionization energy, because if you're trying to keep it, it's going to be hard to remove. Same with the flip side. So atoms with low electron affinity, so atoms that don't tend to keep their electrons, have electrons that are easier to remove. If you're not trying to keep it, it's going to be a lot easier to remove. So it's actually going to follow the same pattern, but what's different is the logic. So on our periodic table sketch that we are getting very good at drawing, 3, 4, 5, 6, 7. When we denote the trend, the columns aren't important here. We're going to denote the same trend. So electron affinity was highest in that upper right-hand corner. Ionization energy is highest in that upper right-hand corner. So this is going to be our extreme for those electron trends. So I want you to put a big E. This is our extreme for the electron trends. As you go towards that upper right-hand corner, you're getting higher and higher values in our electron trends. And sharpening my colored pencil so I can fill it in. We actually have a third electron trend that's kind of a combination or a mashup of the two. So electron affinity is all about keeping. Ionization energy is all about removing. Electronegativity is all about stealing. So electronegativity is about keeping and stealing it. So electronegativity is the tendency for an atom to keep, remember that's one of kind of our power words in the definition, the electrons it has and steal additional electrons. So we're talking about keeping, and we're talking about stealing. And if you remember, we steal in order to obtain a full outer or a full valence shell. So electronegativity is all about completing that full valence shell. This little detail means there's one large difference between electronegativity and our other two electron trends. So electronegativity is all about how much an atom will change in order to get that full valence shell. Now, if you remember, our noble gases are already at a full valence shell. So noble gases are 0 for electronegativity because they have no desire to steal any additional electrons. So it will also increase towards that upper right-hand corner, but not for noble gases. So the exception, noble gases have no electron affinity because they already have a full valence shell. So they are going to keep the electrons that they already have, but they don't need to steal any more. So they're going to have a 0 value for electronegativity. So electronegativity is going to be high again in that upper right, except for you kind of got to cover up the noble gases. They're going to be a 0. For these electron trends, you're probably already noticing, with this one exception, all 3 electron trends follow the same pattern. What is different is the buzzwords that you're going to use in your explanation. So the logic is different. So they're all the same pattern, but we're talking about different logic. So for electron affinity, we're talking about keeping. So in your definition or in your explanations, I'm going to be looking for the word keep, or Mrs. Beek's going to be looking for the word keep. We're looking for that specific term. Electronegativity is about keeping and stealing. We're looking for those 2 specific terms. Ionization energy is about removing. We're looking for that specific term. So when we're asking questions about electron trends, questions like which is going to have a higher or lower value, that's going to be the same no matter which trend you're looking at, with the exception of noble gases. What's going to be different is your explanation of why and the buzzwords that you need to use in that explanation. So we're going to go ahead and do some practice questions with that. And let's go ahead and compare. Let's do beryllium. No, I think I use that one a lot. Let's do calcium and gallium. So we're doing calcium versus gallium. So on my cheat sheet, little sketch here. Calcium is right here, and gallium is over here. So we're looking at same row, different columns. So they're spread out further that way. And we're actually going to just go ahead and review all of our trends here. So for calcium versus gallium, we're going to do questions on which has largest atomic, spelled that wrong, which has the largest atomic mass, why, which has largest atomic radius, y, which has highest, what order did we do them in? We did electron affinity first, which has highest electron affinity, Y, which has highest ionization energy, Y, and still on the screen, which has highest electronegativity, and Y. Now, I would suggest you pause your video, try the questions, unpause your video, and then check yourself with those answers. So if you'd like to do so, that's how I think you're going to learn best. Go ahead and pause your video now. All right. Anytime I'm doing a pattern, I start by my three corners. My O, M, E. And I write them every time. My OME, my extremes. So which atom has the highest atomic mass? Well, I can see it. Calcium versus gallium. Gallium is closer to my extreme. Why? Well, our atomic mass logic actually, I'm going to move this closer, never changes. Gallium has more protons and neutrons. Now, our logic number never changes, but sometimes students start to get mixed up when we get into the electron trends, and they start talking about protons and electrons. Make sure you're keeping atomic mass straight. Atomic mass is all about those neutrons and those protons. We're not counting electrons here. Everything else is about electrons, but for here, we are talking about neutrons. So gallium, because it has more protons and more neutrons. All right, radius. Well, I can see pretty clearly calcium is closer to my extreme. So calcium is going to have my larger radius. For Y, you're going to need to go back. You might need to go back and check your radius notes. Well, here, they're both in row 4. So both have 4 electron rings. However, gallium has more protons. So it has more protons. It has a stronger nuclear pull. Calcium has fewer protons, which gives it a weaker nuclear pull. So its electron rings are more spread out. And now into our new trend. So which has the highest electron affinity? Well, my problem solving doesn't change. So which has the highest electron affinity? Well, gallium is closer to my extreme. So gallium is going to have the higher affinity. Why? This is where we're going to have to go back and know our definitions. Well, gallium is in column 13 or column 3. So it has 3 valence electrons. It's 5 away from a full shell. That's a lot, but it's 5 away. Calcium is in column 2. It is 6 away from a full shell, so it's even farther away. So gallium is actually closer to a full valence shell. So gallium is closer to a full valence shell. Therefore, it tends, and here's my buzzword, to keep its electrons more than calcium. Now, both atoms tend to form positive ions. So both atoms tend to actually lose electrons, but calcium's going to lose them just a little bit faster because it only has 2. So it's going to lose them just a little bit faster. It's going to be a little bit more reactive than gallium. But what I'm looking for when I grade is answer right, talking about valence shell, use the word keep. Check, check, check. You're good. And then which has the highest ionization energy? Well, remember, our pattern doesn't change. So gallium is still going to be closer to our extreme, so it's going to be gallium. But ionization energy isn't about keeping. Ionization energy is about removing. So gallium is closer to a full valence shell. The closer you are, the more you keep it, so the harder it is to remove the electrons. So its electrons are harder to remove. Again, I'm looking for the right answer for you to talk about valence shell and use the buzzword, use remove. All right, last one, which has the highest electronegativity? Well, same pattern, same extreme, still going to be gallium. But now we're changing our focus, we're changing our buzzwords. So gallium is still closer to a full valence shell. So its electrons, and now we're using our buzzwords, we're using keep and steal, are kept more frequently than calcium's. Gallium has a higher tendency to steal the remaining electrons it needs. So higher tendency to keep, higher tendency to steal because it's closer to that full valence shell. So the answer doesn't change unless there's a noble gas in the mix. The answer doesn't change, the logic changes. So you got to make sure you're tying the right buzzword to the term. So go ahead. I wrote big. You might have room, but I'm going to give you one more example to do on your own. Same questions. I am just going to have you compare. So we did same row, different column. Let's do same column, different row. So let's compare oxygen and, is that selenium? Selenium. So oxygen and selenium on my little mock periodic table. They're both in column 17. Nope, 16. Oxygen is on the top, and then selenium is down in row 4. So I want you to go ahead and answer those same 5 questions for oxygen and selenium. If you don't remember the questions, go look on the previous page, but my computer's about to kick me off of recording.